Okay, today we'll be discussing about accessing model accuracy in supervised learning. Okay, we'll be mainly discussing about in terms of regression settings. For classification and other kind of supervised learning, we have other measurement which we'll be discussing accordingly when we'll discuss about the classification algorithms and others. Okay, so there are certain key concepts by which we can determine the model accuracy. That means how the model is performing and how it is fitting the our underlying system or underlying data, right? So we'll be discussing those key concepts today, which will basically tell us how the model will be performing or how the model will be better fit to our data. Okay, the first thing comes into in picture is called irreducible error. Okay, so now irreducible error means when we prepare the data, right, sometimes it may happen that we may not be able to capture some of the features, right, which have better impact on the output function. Okay, it may happen, or it could happen that when we were uh, preparing the data, right, there could be a measurement error as well, right? Now this leads to this irreducible error. That means this particular error will always be there in the system. That means our output function will always have this particular error. That means we will never be able to be 100% perfect. Okay, so this error cannot be reducible. That's why it is called irreducible error. Okay, well, generally we mention it as a epsilon. Now the second error comes into picture, and which is very important, is the mean square error. Okay, now this is how it is defined. So what we are doing it basically from each and every observation point. Okay, observation means our data. If I just show you our graduate admission data set, so this was our actual chances of admit, right? And this one was our predicted chances of admit, right? So we are subtracting these two, okay, and taking the square and take the average. So that is we are defining as a mean square error. Okay, so as the definition telling, where my f bar is my predicted output for ith observation and yi is my actual output for the ith observation, and n is my total number of observation. That means training set. Now if you see, there is an interesting thing happens over here in the definition of MEC, right? So if I go to the next page, if we carefully see the MEC definition, it's basically defined on the training set itself, right? Now if you remember from our regression regression details, when we worked on the math behind the simple linear regression or multiple linear regression, what we have done, the error function we have defined is the same as this guy over here, right? See this guy over here. We basically took for each and every observation, we took the difference and squared that and sum them up to define our error function over here. So when we determine the model equation or the line in terms of linear regression, when we determine the line which is basically fitting the data, we basically minimized this portion of this particular equation, right? So that means there is a high chance that training MSE will be always low, right? We call it training MSE because this MSE is defined on the training data itself, right? So so it looks like training MSE may not be the good measurement for the model accuracy. What could be the good measurement is the test MSE, where we calculate the same mean square error for the test data itself. Okay, so that means test means unseen data over there. If you remember, when we did this particular model fitting, we took 70% of the data as training data and less 30% of the data as test data. If for those 30% of the data the MEC value is becoming low, that means our model is somehow okay, good performing, right? So that should be our actual measurement. Now this leads to another problem. So let me go back. So So we established that the low our test MSE, the better our model accuracy will be, right? Now the problem is we may not have always access to the test data. Now think about a stock price prediction, right? So until and unless tomorrow is coming, I do not know the actual stock price it has predicted, right? So that means I have very less or actually no access to test data over there in the stock price prediction, right? So in this case, what we should do, because we won't be able to determine the test MSE over there in that case, right? So what could be our alternate options over there? Okay, let us discuss about them. One could be like, then the training MSE is sufficient in those kind of scenario. Let us determine that one. Okay, so for that, let us talk about a scenario over here. Okay, so let us see, this is this black color graph. If you see, let us think about, this is our actual data set. That means this is our actual function which basically representing our data. Now on that we have applied our either our linear regression, and also I did not talk about non-linear regression. Um, so we will just touch base on that. Okay, when we'll discuss about non-linear regression, we'll discuss more details how to generate this kind of graph as well. So over here, if you see, the black color one is our actual function, data function. Okay, so now through linear regression we come up with this orange color graph, orange color line basically, which is fitting the data. Now with non-linear regression, there could be a lot of different kinds of non-linear regression. We can come up with a blue color line like this, okay, or a green color line if you see it over here, which almost touching all the data points over there. Okay, now there is a concept called flexibility here. Okay, flexibility means the model which will represent the underlying data will be very sensitive to the data over there. That means it will try to accurately fit the data. If you see this particular green color line, it is too much flexible because almost it is touching all of the data points over there. But while doing that, it is actually not generalizing the particular model. So it is trying too hard to fit the data. Okay, and now if we talk about this orange color line over here, it's very much less flexible because it is almost not touching any of this point. Okay, so we call this green color one is a overfitting of the data, and this orange one in this particular scenario it will be underfitting of the data. Okay, now the blue color line, if you see, it is achieving two things. Okay, it is generalizing the whole data underlying system, as well as it is able to capture some of the irregularities in the data itself. If you think about this orange line over here, it is not able to capture some of the irregularities of the data because our actual function is non-linear in nature. Okay, so this leads us to a graph called MSE and flexibility. If we graph it, you will able to see some pattern over here. Okay, now in terms of flexibility, if you see, the orange color has very less flexible one, right? For it, the test MSE is this red color line, and the training MSE is this green color line. Okay, for them it is both are too high, but test MSE is still too high compared to training MSE. Okay, now when we talk about blue color line, if you see, the test MSE is getting decreased and decreased. Even training MSE is also getting decreased a lot. Okay, now when the model is becoming more flexible, if you see, there is a certain uprise in the test MSE, but my training MSE is becoming low and low because of this scenario, because of this particular scenario where the MSE we defined in such a way that the equation we use to define the MSE is actually the equation we minimized when we fit the model, right? So that's why if you see, the training MSE and test MSE are telling me two different story at all, right? So training MSE looks like it may not be a proper measurement for the model accuracy. Okay, let us take a couple of other examples over here. Okay, so let's talk about this one where my actual function is linear in nature. Okay, similarly we come up with our orange line with linear regression with some more flexible blue line and more flexible green line over here as well, almost touching most of the data points over there. Again you will see the similar kind of behavior over here. Okay, always my test MSE is higher than training MSE. Initially when the flexibility is very low, then both of them are very nearby, right? After certain point, when I am increasing the flexibility, the training MSE is getting lower, but my test MSE is getting also lower. My training MSE is getting more lower. But when my model is becoming much flexible, the test MSE is suddenly going up, but my training MSE is going down only. Okay, so that means we are establishing, maybe we'll take another example over here as well, when our actual data is non-linear in nature. Same thing is happening over here. That means, so my training MSE, I cannot replace that with the test MSE. So training MSE cannot be a good measurement. So that means we need to come up with some idea about how we can determine the test MSE, okay, or at least some idea which governs the test MSE by which we can take certain kind of decision. Over here, if you see it, to fit this particular data, we come up with three different kinds of model over here, right? So if we have some measurement about test MSE or some idea about test MSE, we will come up with which model is the best for this particular data, right? So this leads us to a very important concept in supervised learning called bias-variance trade-off. Okay, so before we talk about bias-variance trade-off, we will try to understand certain key concept over here. Okay, so one of the key concept is expected value, another is bias, another is variance. Okay, now what is expected value? Now in probability theory, in statistics, right, what is random variable? Basically when you do some kind of experiment, let's say we are rolling a particular fair sided die, right? Now, and if we just determine what is come up with the top surface of the die, what number is coming up, that's an experiment, right? And for each and every experiment, if we take that number and assign to a variable, we call it random variable basically. So the random variable can take the values of 1, 2, 3, 4, 5 and 6, right? So if we do this particular experiment infinitely, like, okay, and take the average of it, so basically that average value is our expected value. Okay, now it can be proved that those average value is actually represents or actually converges to the mean value of this whole whatever value random variable this particular random variable can take. That average value, if we take, that means average of 1, 2, 3, 4, 5 and 6 is 3.5, right? And if we just do this experiment and come up with the expected value of this particular random variable x, we can see the expected value converges to 3.5. Now how expected value is defined? So mathematically we calculate something like this. Okay, so for each and every possible values of random variable, that means 1, 2, 3, 4, 5 and 6 in this particular scenario, we first multiply with them with their probability, right? So that means if we just roll a die, so the top surface for each and every number to come up, there's a probability of 1/6, right? Because there are 6 possible outcomes of this particular experiment, right? And one of them is coming, so it is probability is 1/6, right? So if I just multiply each and every possible outcome with 1/6, okay, and sum them up, okay, we will get the expected value over there, 3.5. If you see it over here, which is exactly the mean value over here, okay, which is 3.5. So expected value, we can think of it is, say, estimation of an mean value of a large number of events or large number of experiment values, experiment outcomes, or large number of values of a particular random variables. Okay, now expected value, why we are discussing it? Because we need an estimation of test Mse over here. Okay, and as we discuss, the test Mse is very hard to determine, right? So we need some kind of measurement for our test Mse. We will see how to do that one. Okay, now let's talk about variance. Now variance basically represents, so suppose over in our supervised learning, what we are doing it over here, right? We basically take a training set and try to come up with a model equation which fits the data, right? Now if we work with a different training set, okay, for similar kind of data, it could happen that the output function will be substantially varying. Okay, if it is substantially different, we call it a higher variance. Okay, otherwise we call it a lower variance. That means variance refers to the amount by which our output function will change if we estimated using a different training data set. That means our output function is very much sensitive to the training data. Okay, now in informal terms, variance are basically representation of how numbers are spread out from the average value. So to determine that, let's talk about these two particular data set. We have 5 numbers, 8, 9, 10, 11, 12, and another set we have -10, 0, +10, 20, and 30. If we take mean value, right, so just sum of them divided by 5. For this particular data set we have 10. For this particular data set also we have mean is 10. That means both of these two data set we have mean value 10. Now how variance we calculate? Variance we calculate for each and every data point. We basically subtract the mean, take a square, and take the average of it. Okay, now if we do that one, okay, for first data set the variance value come up 2. Now the second data set the variance value come up 200. That means for the second data set the values are more far away from the mean. Okay, that is what variance is telling us about. Okay, how the values are sparsed from the mean value. That means if you think about it, if we think about these two data set as two different training data set, if we have a higher variance, that means our output function is too much sensitive to the data, right, over there. Now let's do some kind of analysis on the variance, more analysis on the variance mathematically. Okay, so variance we talked about, so mathematically is defined as the expected value of the square deviation from the random variable from its mean, right? That means expected value we represented as E, right? This is our random variable X, and if we take mu as its mean, that means X minus mu whole square, that is expected value of this one is our variance, right? So if I just now previously we talked about when we do an experiment fairly large amount of time, that means infinite time, our expected value converges to mean. That means mu I can write it as expected value of X only, right? That is what we have written it over here. And if I just work on the square, so I can write x square minus 2x into expected value of x plus expected value of x whole square, right? So then I can distribute this expected value among all these three things, right? So that means expected value of x square minus expected value of 2x of expected value of x and expected value of x squared, right? Now if you think about it, when we talk about random variable, then only expected value makes sense, because that random variable for each and every experiment will have some kind of value, and then we are basically taking the average over there. That means basically expected value makes sense only when we talk about a random experiment and random variable. Now for 2, it's a fixed number, right? It's not a random variable, so expected value of 2 is always be 2. That's why 2 can come out over here. Similarly, expected value of x and expected value of x over here. Okay, so now if I just write it, this one will be expected value of x and expected value of x. Okay, now this guy again, expected value of x will be again a number, right? Because if I just show you over here, expected value is actually a number for a particular random variable, right? So expected value of x is actually x, just like expected value of 2. That's why this particular uh, equation term will be becoming 2 into expected value of x into expected value of x. So that is what we have written over here. Okay, now again the same concept applies over here as well. So it is again expected value of x whole square. So ultimately we are ending up with expected value of x square, then minus of expected value of x whole square, because 2 minus 1, right? So variance formula can be determined something like this. Okay, this will be helpful in latter part of this particular video. Now let's talk about bias. Okay, now in variance we talk about how the model is basically sensitive to the training data, right? Now bias refers to the error that is introduced by the approximating of the real life problem, just like this guy over here. Over here the actual function was non-linear in nature, right? But we assumed when we implemented the linear regression, okay, we assumed that there is a linear relationship exists between the variable we are predicting and the features, right? So this particular assumption itself cause an error, right? So that is called the bias. Okay, so that means bias actually refers to the error that is introduced by the approximating a real life problem. Okay, now mathematically the definition of bias is very simple. It is the expected value of output minus the actual value. Okay, now we introduce three terms: expected value, bias and variance. Okay, now there is a reason behind this, because one of the reason is we want to determine the expected value of test MSE. Okay, and we'll see it in future. Expected value of our test MSE is actually dependent on the bias squared plus variance and the variance of the irreducible term. Okay, so that means it's directly dependent on the bias and variance. The higher the bias, the lower the model fit will be, right? Or the model accuracy will be. Again, the higher the variance, the lower the model accuracy will be. And anyway, we cannot reduce this irreducible error. That means the model will always have the irreducible error. That means if we if we want to model a particular system or data set, right, using various kinds of regression model. So if I just go back over here, a particular this data set we modeled using three different things, one through a linear regression and two non-linear regression. Okay, now if we think about this variance trade-off, we have to select that model which always have less bias and less variance because of this particular equation over here, because over there we can see our expected value of the test MSE is actually directly dependent on them. And if you see it, this particular these two graphs is actually depicting this one. For the blue colored line, right, it's less bias because it's almost telling me, almost fitting the actual function itself, right, the same way, right, and also it is less variance as well, right. So that's why if you see till the blue point the test MSE was decreasing. That means test MSE is actually the lowest till the blue point. When I am increasing the flexibility, again my test MSE is going very high. Okay, but still my training MSE is going down. Anyhow, training MSE is not a good measurement for our model accuracy. Okay, so in future videos we'll see this bias variance trade-off. Okay, this bias variance concept is actually founding the basis of ridge and lasso regression. Okay, we'll see that one as well. Now for now, let us consider on how we can come up with this one. Okay, so for that, let's suppose that we have a training data set, okay, consisting of our x1, x2, xn value, and we have corresponding real value as yn associated with that point x1, just like our simple linear regression we have it, right. We have for a particular feature x1, x2, x2 values and their corresponding y values. Okay, so and we assume that there is a function with noise. This is our actual function. Okay, and epsilon is our noise, and we will also assume that this noise has mean as 0, okay, and variance as sigma squared. Okay, and we want to find our output function f bar x, right, that approximates our actual function fx by means of some learning algorithm, right. And we want to basically determine the MSE of between y and f bar x, right. That means basically we want to determine the expected value of y minus f bar x whole square, right. If we see it over here, we have not divided by n. When we discussed about actual MSE over here, we divided by 1 by n because here we are talking about expected value, which is basically an average, right, ultimately approximating an average over there. Okay, so if we have this particular MSE, okay, so that means this is MSE needs to be minimal both for our training, which we have seen it is for training it's always minimal, right, but it has to be minimal for points outside of our sample as well, for the unseen data. Okay, now as we have always have our irreducible error, so that means we always have some kind of error in our prediction, but that's fine. But the reducible error we can minimize it, right. Now let us work on this particular proof of expected value. So we can write, so for simplicity what we'll write it out, our main function f is fx equals to f and f cap equals to f cap x, like our main output function. Okay, so if you remember when we discussed about variance, right, we proved these things. A relationship between variance, the random variable, right, and their expected values. Okay, so this is the same thing I have written it over here. Okay, and just if we just shuffle it out, so expected value of x square will be variance of x plus the variance of x, expected value of x whole square. Now our f is a deterministic, so we will always have expected value of f is equals to f. Deterministic means if you run f for a particular value, that means if I just go back over here, okay, so this is our output function, right? F over here. So if we run f for a particular x value, it will always give me that value itself. Okay, that's why the expected value of f will be f over here. Okay, and we have our main output variable y equals to f plus epsilon, which we have determined. So if I just show you over there, which we have defined over here, right? Now what will be the expected value of y if I just apply expected value on both side of this equation? So right side will become expected value of f plus expected value of epsilon. Now we have just determined that expected value of f is f, and expected value of our epsilon is 0, because if I show you the assumption over here, is we have assumed that the epsilon, the irreducible error, has 0 means. That means as expected value always converges to mean value, so that's why expected value of epsilon will be 0. That is what we have determined over here. That means my expected value of y will be f. Okay, these things will be handy when we will solve the equation. Let us move to the next page. Now another thing will be the variance of epsilon. We have also assumed that variance of epsilon will be sigma square, right? So variance of y will be expected value of y minus expected value of y whole square, right? Now as variance, if I just refer it before, right? So variance of x is the any random variable, then the mean, right? So that is what I have written it over here as well. The y minus the mean of y, which is basically expected value of y whole square, right? Now expected value of y we just now determined. So if I just refer it the same page over here, expected value of y we have determined as f, right? So that is what we have written it over here, y minus f whole square, right? Now y we have determined as f plus sigma, that is what we have written it over here. So this is becoming expected value of sigma square, right? Now variance of y is equals to expected value of sigma square. This is also another thing which we will be using in our equation. So now also we have determined expected value of x square, right? Before, using the variance formula, which is variance of x plus expected value of x whole square. So that is what we have written it over here. Variance of sigma plus expected value of sigma whole square. Okay. So that means our, as we proved before, now variance of sigma is, so variance of epsilon will be our sigma square, as we have assumed it over here, right? Before, variance of our sigma term will be variance of epsilon term will be our sigma square. So that is what we have written it over here. Now expected value of sigma is 0 because of this mean is 0. So ultimately it is becoming sigma square variance of y. Okay, this also will be using in our Mse formula. So now we are determining the Mse value, right? So Mse value means the y value, that means actual value minus predicted value whole square of an expected value of that one, right? So if I just replace y with f plus our epsilon, so this equation is becoming f plus epsilon minus f bar whole square. Now if we just add expected value of f bar and minus expected value of f bar to this one, so the end equation is becoming same over here. Okay, so what we'll be doing, we'll be taking f and f minus expected value of f bar in one, and then expected value of f bar minus f bar in another one, and sigma is another term. So that means it is becoming a plus b plus c squared, right? So that is what I have written it over here. So it's a square plus b square plus c square plus 2ab plus 2bc plus 2ca, right? So we will simplify these terms. Okay, so for that, what we have done now, I have just distributed this expected value over here. Okay, nothing fancy is going on over there. Now let us work on this term by term basis. The first term is expected value of f minus expected value of f bar square. Okay, so that is what we are simplifying now. So if we just simplify the square term over here again, so this is becoming this guy over here. Okay, nothing fancy. Again, I am distributing the expected value over here. Okay, now as f is deterministic, right? That means expected value of f square, I can write expected value of f into expected value of f, right? So ultimately expected value of f is my f, right? Because we have determined over here as f is deterministic, if expected value of f is f, so ultimately it is becoming f square, this particular term, right? Now for this term expected value of f is becoming f. Now expected value of f bar, previously as we have discussed, this is a particular term, right? This is not a random variable, so this can I can directly write it is equals to expected value of f bar. Similarly, this guy as well, when we talk about expected value square, that means we're talking about a particular numeric term square, so that can directly come out expected value of that numeric term is numeric term itself, right? So now if you think about this one, this term is actually f minus expected value of f bar squared, right? Now what is this guy over here? If you see the definition of bias, okay, bias is expected value of our predicted term minus my actual term. So this is what is over here, right? So I can directly write this is my bias square, right? Now let's talk about the second term, expected value of sigma square. So if I just refer it over here, or actual equation, the second term is expected value of sigma square. Now expected value of sigma square we already determined over here is the variance of y, right? Because variance of y, while doing this calculation we came up with this guy over here, right? So that is what we have written it over here, variance of y, which is nothing but sigma square, which we have proved it over here as well. Okay, so let's talk about the third term over here is this guy, expected value of f bar minus f bar square, right? Similarly, we are just expanding the square over here, then distributing the expected value over here. Now by applying the similar concept, I can write this guy directly to expected value of f bar squared. Similarly, this guy is unchanged. Now this guy I can write directly expected value of f bar, and this is expected value of f bar, right? So this is actually expected value of f bar square, right? This is I have written it over here. Now there are another expected value of f bar square was there, that's why it is minus. That means this guy, this whole term over here minus this term over here, right? That's why this term over here, right? And then this guy is this one. Now if you see, this is actually the variance term. If I just see the variance formula, previously we have determined variance of x is expected value of that particular x squared minus expected value of x whole squared, right? So that is what we have it over here. That means I can directly write this one as variance of f bar, right? So for our this equation, the first term becoming bias, second term is our sigma square, that means the variance of our this term, and third term is actually becoming my variance. So the my rest of the term should be becoming 0. So that proof only we have run it over here. So if we just expand the similar way and apply our logic over here, you will see everything is cut over here, okay, cancel out. So it is, this whole term is becoming 0. So that means we can write something like this, right? Our expected value of test MSE is bias squared sigma squared, that means the variance of our epsilon term, irreducible error, and the variance of our F bar, right? Now if you see, good test set performance of a statistical learning method requires low variance or low bias because of this particular equation, which we have discussed this before as well, right? So this is this is called bias variance trade-off. So this is very important when you are applying multiple regression. It could be linear, non-linear as well, for a particular data set to determine what is the best suitable model for this particular scenario. We can think about this bias variance trade-off as well. We should be selecting the model which is less biased and less variance. Okay. Now let's move on. Let's talk about other measurement which are also important for determining the model accuracy. Okay, so these are another kind of measurement we can do, like explained variance score. So this is defined something like this: for each and every actual value minus predicted value, if we take the variance of it, and if we take the variance of the actual value and 1 minus that one, okay, so this is called explained variance score over here. The maximum score is possible as 1, as you have seen it over here. This term cannot be greater than 1. The more it close to 1, the better the model is. Okay, so when my explained variance score is very close to 1, I can say the model is performing better. Similarly, we have mean absolute error, and if you see, when we talked about mean squared error, we basically squared this term, right? For each and every term, the actual value minus the predicted value. Here we are just taking the absolute value of this particular term and then the average. Okay, similar kind of concept. Okay, mean, this is called mean absolute error. Okay, and there is another one which is very much important called R2 score. Now R2 score is defined as, if you see the numerator, okay, it is our MAC, right? One part of the MAC where we have YY minus YI bar, that means our actual value minus the predicted value squared. Okay, then we are summing them up, correct? And in the denominator we have yi minus the mean value. Y bar is nothing but our mean value. That means all the observation value, and then we are taking the average of it, right? Then the squared of it. Okay, this is basically the variance, right? And if we just 1 minus this particular fraction, this is actually becoming my R2 score. Okay, so this is also another measurement, and maximum, even here also, if you see, the maximum value can be 1 only because of this particular equation, and the more it close to 1, the better the model accuracy will be. Okay, so we talked about some of the measurement which are the very basic measurement uh, in regression settings for to determine the model accuracy. In future we will see some other measurement as well which could be more better compared to this particular settings, but for now this basically setting up the ground for to determine our model accuracy. Okay, so in future we will talk about more complex stuffs. Hopefully this is helpful to you guys. See you in next video.